started. Because here we go. Uh-oh. Chapter 6. Wait. I told you, after we get done with linear programming, that every chapter kind of stands on its own. Like somebody could walk in right now and even though they haven't done any of chapter 1 through 4, and still be able to get these future chapters. Knowing linear programming helps, but they all stand on their own. They're all separate kind of jobs in the real world. For example, right before this chapter 6 lecture, I always jump on the internet to see what I can find in jobs. And I forgot where I put it. Here we go. That's not even the one I'm going to read. This is it. Here's the one I found this morning. The key word is the job says logistics. And logistics is a supply chain management type job that's all about helping the company you work for save money on their expenses related to shipping goods and receiving goods. It's all about saving them money. And so here's a job I found. It happens to be in Canton, and it says this is a logistics coordinator. This is the kind of job that you want, if you're a supply chain management major, that you would want to get right out of college as an entry-level job to get experience. This is the perfect one. Yeah, it says down here you have to have your bachelor's degree, either in supply chain management, logistics, or some kind of applicable studies, equivalent work experience. So if you don't have your degree, but it's a great entry-level job because it's easy. You get to see exactly what happens in logistics. How do they plan on getting things shipped out and shipped in? What was it I wanted to read on this one? It was description of your job. Afternoon, it's an afternoon job. You get to sleep in. That's got to be appealing. When I was your age, I'd give anything to sleep in. Now the sun comes up and you're out. Afternoon logistics coordinator at this company to provide support to the logistics department while monitoring project progress and dispatch phone. That's the worst part of it, because the calls are coming in so fast, and you're having to call the drivers of different trucks, and you're having to coordinate everything. Receive customer orders and process the orders to dispatch sheet. Maintain various logistics spreadsheets, track and compile daily order totals, distribute and track all issue tracking rates. Every day, it's the rates, shipping rates for everything that has to go out. Now, from my experience, I want to tell you a story where I was working for a manufacturing company down in Ohio called Artesian Industries. Before the word logistics was even invented, I had never heard of this word back in the 1980s. And we had a person who did this exact thing. We never called her logistics, but we called her gold. Because the amount of money she saved the company. I happened to be at a company that we owned our own trucks. It's rare for manufacturing companies. They'll usually send out subcontract trucking all the time. So you're working with different trucking companies that happen to be in the area that have routes already going out. But we had our own. And the logistics person worked with the warehouse coordinator to the point to where when we're ready to load a truck, every single piece of item was planned in advance, so it's packed to utilize the footage in the truck as much as possible. It's all about using every inch possible, because the more you get in the truck, the more money, the less it costs you, is what I want to say, for the shipment. The more you can get shipped. A truckload going out has more value if it's completely full than if it has empty spots all over the place. Here's the other thing they also had to plan. They knew exactly the route the truck was taking to deliver all these goods. And it had to be packed with the last customer in the front of the truck. And the very first stop is in the back. So when they go to that first stop, they're unloading right there at the very back. And the next stop is ready to go right in front of that. And then they unload that. Then they go to the next stop. And the very last stop is in the front of the truck. And then what happens is, we would have empty trucks start driving back. And this would be so expensive. And our logistics, where she made the company money, is she was out there calling all these different companies that we do business with and saying, hey, do you need anything coming back to Ohio? We were in Mansfield, Ohio. We were, anything coming back to Ohio? Because we got a truck coming by your place. Do you have anything? And she would line up things to ship back, and we would make money on that. Because bringing an empty truck back is very expensive compared to picking up orders on the way back to bring back to Ohio. So they would subcontract our truck to get their goods to Ohio. That's what logistics does. That's how you pay for yourself. At this point, a company like this, they're already shipping goods. They already have goods shipping in. How do you save them money? In this particular job, you're entry level. You're learning how everything's being done. And you're the go-to person to go get lunch, answer the phone, and all this. But you're learning how everybody else is doing it. And you'll start seeing this person's on with 3 different trucking companies all day long, trying to line up exactly what the cost is going to be. Getting the price from this one. What do we ship with this one or that one? Usually, they don't have their own trucks. So they're trying to get the best prices they can from trucking companies. They either already have trucks going in the direction that they need to get goods to. That's what logistics is. Now, when you then get promoted, where you're doing the actual scheduling of shipments going out and coming in, you've got to know transportation and transshipment. Because if you don't know how to enter the numbers into the software correctly, then you're not getting good results that will save the company money. It's all about how, while these numbers are being entered, that saves the company money. So that's what we're at right now. You're going to learn the basics on how to come up with the numbers to enter into these softwares that will allow you to save the company money. It will give you the absolute least expensive way to get those goods where you need it. The first one's called transportation. Let me get to it. Right here. I want you to look at this. This is transportation. The word transportation model is all about we need to get goods from up here to wherever it needs to go because of demand usually. In our case, the company I work for, we were one of the few manufacturers that would ship out right to the customer with bypassing the distribution centers. And that was a big deal for customers, and that was how we were able to compete with the big ones, is because we skipped distribution centers and we would have lower minimums you have to order to be shipped directly. So that was a big deal with our customers. What you're looking at are, here on the left is where goods are coming from when we get to the story. On the right is where they need to go to. These numbers here in the story will say this is how many they're asking they need shipped here. This is how many. These numbers on the left, if we're shipping from Cleveland, this is all we have available from capacity. If we're shipping from Belford, this is all we have. And so this is the most you can ship out, but we don't know what would be the least expensive way to get it to these 4 customers at these amounts. These numbers on the lines, that's the cost for each item being shipped from one location to another. So if I said to you, hey, if you're looking at this transportation network and we need to ship something from Bedford to St. Louis, what's the cost for each item we're shipping? Anybody see it? That's right. Follow the arcs. Bedford to St. Louis, you see the arrow? There's a 2 on it. $2 for every item we ship there. That's pretty cheap. So now you see the demand, you see the supply, you see the cost. If you were doing this without a software, you'd go, okay, what's the cheapest I can get stuff to Boston? What's the cheapest I can get stuff to Chicago? And you keep working it. Here's a $2 item. Here's 2 for every item. You found 2 of them with 2s, or here's another 2, but there's already stuff going to Boston up there, so I got to go to the 3. Is that a 3? What's that? Is that 3? So I got to go to the 3. Instead, because in real life, you don't have just 3 places to ship from and 4 to ship to. You got 3 places to ship from and 12 or 20 to ship to. So you just can't do it. Instead, you've got to know how to plug it into the software, and it will tell you exactly how many should come from Cleveland, go to Boston, go to Chicago or St. Louis, out of Bedford, out of York, and here's the least amount it will cost you to supply these demands. That's what transportation is all about. Now, I want you to look at this. Right here. This is called transshipment. Transshipment is just like transportation, except the story always says that the goods have to be shipped somewhere and then continue on to somewhere else, to the end customer. If the story says stuff has to be shipped somewhere and then shipped again, that's transshipment. And you will have these middle nodes. These are distribution centers in this story. So we have 2 places from and get to 4 customers. And if we had just these 2 in the story, it would be transportation. But in this story, it's talking about how we're going to distribution centers. It breaks up into smaller quantities, then ships out to our customers, transshipment. Now look at this one. Hey, hey, hey. Am I hitting the wrong button? It looks just like transportation, doesn't it? Look at the ones. Everybody see the ones? This is the difference between transportation and assignment. And people will get confused because you're going fast on your quiz. But the story on this one says, whatever is supplied on the left, only one gets to a client. And the client only needs one. That's called assignment. 1 to 1. In this case, I think the story is about we have these project leaders. We want to assign the project leaders. We have these 3 projects for clients coming up. And we're trying to figure out which project leader would be best for each one of the clients to keep our costs as low as possible. That's assignment. Now, if you have the list of topics anywhere, by chance you printed it, somewhere in your notes, this is very important to write down. Every one of these I just showed you have nodes and arcs. Nodes are the circles, arcs are the lines. And when you're hearing the story, wherever something's coming from are nodes. Wherever something's going to are also nodes, the receiving nodes. But you're going to get the story, you have to draw this. Then you have to convert this drawing to a linear programming, objective functioning constraints. But I'm going to break it down to where it's so easy. Every time I'm on this chapter, you're going to walk out of here going, oh, this was easy, I remember this. Then we don't have any homework. So if we did have homework and you wait a couple days, the most common thing I hear is, man, I had this down at the end of class, and now 2 days gone by, and it looks like a foreign language to me. There's no way I can figure this out. But yet it's so simple. So simple. I'm going to break it down to what I used to use to simplify this completely. Every node is a constraint. That's the key to break this down. How many constraints do you see in this problem? 6. There's 6 nodes. Every node is a constraint, period, for all of these. The ones for next Thursday, every node is a constraint, all right? How many constraints do you see here? 8 nodes. 8 nodes, there should be 8 constraints, get it? Okay. Every arc is a variable. Every arc is a variable. So I want you to look at Dallas. Well, that's a bad one. Let's go with Detroit. That's a good one. Detroit. Detroit is a node, so it's a constraint. But there's variables involved in that constraint. And for you to know how many variables to include in that constraint, you count the arcs touching that node. How many variables are in the Detroit constraint?
2.
That's right, 2 variables on the left. Detroit, what's the amount of demand for Detroit? 200. There's your right-hand side of the constraint. So has everybody got this? Nodes are constraints, arcs are variables. Everybody. Okay, let's go back to this one. We got it. Not that one. This one. How many variables exist in this problem? Let me stare at it for a minute. Okay, got it. How many variables exist in this problem?
12.
You see how many arcs? That's all you got to do. Count the arcs. There's 4 coming out of 3 different nodes, so that'd be 12 variables, right? So you know there's 12 variables. There are 12 variables in your objective function. That's how you know to write the objective function. You just count the arcs. Go ahead.
Maybe I'm missing something, but aren't arcs all the circles there? Or
No, the circles are the constraints.
Nodes.
The nodes are the constraints. The circles are nodes, which are the constraints. So we have 7 constraints, but the arcs are these lines, and we have 12 of those. There's 12 variables. Here, all of these transportation networks, for as long as I can remember, always use X, this number right here, and that number right here, always represents where it's coming from, where it's going to. Where is it coming from, where is it going to? So if I pointed at any arc, you should tell me what the X is. Because notice each node's been numbered. So I've pointed at this arc right here that has a 4 on it. See this one right here I'm pointing at? That would be X what? Wait, I can't hear you. I'm pointing at that 4 right there. See that arc, that line? That would be X what? Trevor, you had it? Go. Stop. That's the cost. What is the, it's always the first numbers, where it's coming from. What node is it coming from? 3, which is yours. And where is it going to? Which is number, what node is that? This is X, 3, 3. Okay, the light bulb is time. Ready? Let's do another. Right. That, now this 5 right here, everybody see that 5? That is X what?
2.
Oh my God. You got it. That's how easy this chapter is going to be if you get these fundamentals down. I'm purposely not telling you the story yet, because the story will make much more sense if you understand how these are designed. If you understand what these all mean. All right. Got to go another step. Are you ready? Look at a node. And if I say to you, we're going to write a constraint for a node, the right-hand side is either the amount it can supply or the amount of demand, depending on what node we're doing. I want to talk about St. Louis. So St. Louis has a demand of one less than equal, because we have to, really it should be equal. What am I saying? Jeez. We have to meet demand. We will not let our customers down. If we can't meet demand because of whatever reason, then Thursday you're going to learn we would add a dummy node to make sure all the demands meet. But really the dummy node is telling you who you've got to inform, they're going to be on back order. And that's the worst scenario. But what did I just say? I can't remember. Was it St. Louis?
Yeah.
St. Louis, what's the right side? I can't hear you. Thank you. There it is. The left side are variables. How many variables should I have on the left for St. Louis node?
3.
Because there's how many arcs touching it?
3.
Just give me the numbers where each arc is coming from to where it's going to. X, 1, 3, plus X,
2.
plus X.
3.
That constraint's done. That constraint's all done. That's it. That's it. You never use the cost of the shipping in a constraint. Period. Let me say that again. Never use the numbers on the arcs, which is the cost to ship, in a constraint. Only the variables on this whole chapter, in logistics, only the variables have, only the, what am I saying? Every constraint never uses those costs, only the variables without their costs. The objective function is where all those arc numbers are going to be inserted. Go ahead.
I got lost with the 1, 3, the 2, 3, and the 3.
Ready? I'm going to
Where
follow.
did that come from?
Here's, right here, we're going to follow the 3 arcs touching it. Coming from 1 to 3, 2 to 3, 3 to 3.
Got it.
Now Alex is going to help me write help me with node 2, Chicago. What's the right-hand side? Equals? What is that? I can't see it. 4,000? Okay, how many variables are on the left side? 3, because there's 3 arcs. Alex, do you want me to pick up? Or no?
No, I'm good.
Okay, now everyone, give me the variables then. X, 1, 2, plus X,
2.
plus X.
2.
That's it. You just wrote the constraint. It's that easy.
3, 2.
Those are multiplying, right?
Wait, what's going on?
3, 2.
Which one did we just do? I'm sorry, hang on.
Chicago, 3,
We're going
2.
Chicago. Should be 1, 2, 2, 2, 3, 2. What do I have?
2, 2, 3.
Hey. Hey.
That one's just going to go with St. Louis. It's okay.
I'm sorry. Start again.
Okay, so how do you just wrote those at 3 and 2? Those are multiplying, right?
No.
No.
We're adding this variable coming from 1 to 2 with this variable, however many are going to be shipped from 2 to 2, however many are being shipped from 3 to 2, however many are being shipped from 1 to 2, wherever the goods are coming from to go to Chicago, it better equal 4,000 items shipped total, because we're meeting that customer's demand of 4,000. We want that money.
Okay, so the number represents where it's going going and coming from, not a multiplication.
Where it's coming from to where it's going to, no multiplication whatsoever. It represents always, for all of these, x, the number where it comes from, the number where it goes to. Now, we're going to do over here, these nodes. Because it's a supply node, we don't have to ship everything. We hope that we make more than we have to ship. We'd like to have some left over maybe for the next following period, whatever it may be. So every time you have supply on transportation, the constraints are always less than equal because we don't have to ship full capacity. This is the most we have, we can make or that we have on hand, whatever this represents, but we don't have to use all of it. So now, I'm going to look at, let's look at Cleveland. Tell me the right-hand side. I just got done saying this is what? Less than equal, and what's the number here for Cleveland? 5,000. Now look at the arcs touching Cleveland. How many are there? 4 arcs. 4 arcs. Since they're all coming from Cleveland, and Cleveland's number 1, I know it's going to be, I can go right now and just do x1 plus x1 plus x1 plus x1. Help me with these, where is it going to? 1, 1, 1, 2, 1, 3, 1, 4. It could go to any one of those. And if we decide to ship from Cleveland to Boston, however many we're shipping, and we're going to ship from Cleveland to Chicago, and Cleveland to St. Louis, and Cleveland to Lexington, they got to add up. They can't go over 5,000 because that's all that can come from Cleveland. But notice the order of the variables are all ones at the start because we're coming from a node of where it's being shipped from. Just like when we're doing a node of where it's going to, the second number is always consistent. 3, 3, 3, 2, 2, 2. Because we're doing a node as to where it's going to. Wait, what was it? Okay.
Question. You said that there's no constant in front of the variables. Is that just for transportation or is that for
all of them? There's no numbers in front of for constraints. Mm-hmm. The numbers on the arcs that you'll hear in the story are all about the objective function. The objective function is the numbers. Earlier I said to you, how many arcs do you see? And you told me there are 12, is that correct? There's 12 arcs? There's 12 variables in your objective function. Max or min?
Min.
Huh?
Min.
That's right. This whole thing is all about keeping the cost of shipping our goods as low as possible. And now you're going to write every variable with its associated cost. I'm starting at the very top arc. That arc would be x what? From where to where is that top arc? 1, 1. What's the cost if I take advantage of that shipment? For every item, I can't see the number. 3. $3, however many we're shipping from node 1 to node 1 on the other side. Plus, I'm going to arc 2. What's the number? Is that a 2?
Yes.
2, so I'm going to go 2 times x, 1, 2. Because I'm following the arc, just going from 1 to 2. The next one is x, 1, 3, but what's the cost? 7, x, 1, 3. Dot, dot, dot. I'm not going to write them all out, but I'll speed them. I can't read the number though. 6 is x, 1, 4, plus 7 times x, 2, 1, plus, is that 5? 3 or 5? What does that mean?
Best guess.
5 times x, 2, 2. 2 times x, 2, 3. 3 times x, 2, 4. And so on and so on. You should have 12 of these in your objective function because there's 12 of them. But what I want to point out, the most common mistake here, is that students will leave the numbers off the objective function and they'll put all those numbers in each of the constraints, which is the exact opposite of what you have to do. So let me emphasize that again. Every constraint for all of these never have those costs. Never have the numbers from the arcs. Only the objective function does. And the objective function has to include every single variable that exists with this associated cost. That's the objective function. There's where the arc numbers go. I saw a question over here. No, no, no. No? You ready for the story for this? Wait. Yeah, hang on. Before we get to the story, I want to make sure you really feel these. You ready? Hey, we're reading the story and our goods have to be shipped to somewhere and then they're going to go on somewhere. And you're going, oh, this is transshipment. And you know this is 3 parts, not just 2 parts. You have nodes in the middle, nodes on the left for supply, nodes on the right for demand, and nodes in the middle. Now, everything I told you about transportation is absolutely the exact same thing for the supply and the demand part of this. Right? Look, for example, I want to do a demand constraint right now. Miami. Miami is demand. Hey. So equals, what is Miami's demand? 150? That's it?
Yep.
How many variables will be on the left? 2, because there's 2 arcs touching it. And they're coming from, it looks like 3, 6, and 4, 6. Is that correct? X, 3, 6 plus X, 4, 6. You just wrote the constraint for Miami. It's just like transportation. Let's do a supply node. Denver, less than equal to, is that 600?
Yeah.
600. How many arcs are coming out of Denver? 2 arcs. There's only going to be 2 variables. Look at the node numbers. 1 to 4 and 1 to 3. So x13 plus x14 less than equals 600. I just did what we just learned about transportation. It's exactly the same. So is assignment. The assignment model, exactly the same. So is shortest route. So is max flow. That's on Thursday. The exact same. Well, max flow has a special meaning, so is shortest route. But these 3, the exact same. No difference. Until you get here. The difference now for the middle, for transshipment, is that whatever goes to a distribution center has to go back out. Let me say that again. Whatever goes in comes back out. So every middle node on transshipment is always equal to 0. Because whatever comes in heads back out. Nothing gets left there at the distribution center for this calculation. How many arcs are touching, I'm going to do Louisville. How many arcs, I got to think here, are touching Louisville, our distribution center number 4? You see 6 arcs touch it, right? 2 on the left and 4 on the right, correct? Now follow the arcs coming from supply to the distribution center, then to the customers. You write the variables exactly like those arcs. I'm going to write 6 variables because there's 6 arcs touching Louisville. I got equals 0, and I got room for 6. You ready? 1, 4, 2, 4. Right? x14 plus x24. 4 of them are going out, the opposite direction. Okay, you ready? What's the first one? 4 or 5? Minus x45 minus x46 minus x47 minus x48 equals 0. I went ahead and made the ones coming in positive and the ones going out negative, but you don't have to do it that way. If you want to make the ones coming in negative, as long as you're making the ones going out the opposite. What's coming in and going out have to be opposite, positive and negative, to get to 0. And whatever you do for one middle node, if you made the ones coming in positive like I did and the ones leaving negative, every middle node has to be consistent with the logic you applied on the first one. So let's do the other middle node, Kansas City. I always like to start over here, equals 0, but how many arcs are touching Kansas City? 6 distribution, 2 coming in and out. And I want to be consistent with what I did with this middle node. So I'm looking at them, hang on, one, is that a 3? Yeah. x13 plus x23, there's my coming in. And then, what is that, 3, I forgot what we're doing. 3, 5, thank you very much. Minus x35, minus x36, minus x37, minus x38 equals 0. Someone else started with putting minus x14, minus x24, plus x45, plus x, plus x, plus x. That's fine. But as long as you do it consistently with the other middle nodes, you're going to get the correct answer. You could flip this. Either way.
Is that in Denver or is that?
This one is Kansas City.
Okay.
Kansas City. Nothing close there, I don't know what. We good? We got that? This is the weird part, right there, that middle note.
So would it be the same as the other one where with drawings of min, you do 3x?
Good question.
Every single one?
That's right. If these are all costs, and we're trying to keep costs as low as possible, it would be a minimization. 2 times x1, 3. 3 times x1, 4, plus, I can't read it, 3? Is that 3? I'm close. 3 times x2, 3, plus 1 times x2, 4, plus 2 times x3, 5, plus 6, is that 6? Times x, I mean, I keep going. It's just like transportation, just like assignment, transshipment. The objective function is the only place that you would put the costs for each possible shipping route that's given. You gotta remember, you may not have this drawing. You may have to draw this from the story, then come up with how to come up with these constraints.
Can you explain to me again why we're using an equal sign in some and a less than in some?
We're using equal sign on demand because the philosophy is we need to meet our customers' demand. We do not want to put them on back order. And the only way to know if they're on back order is if demand is bigger than supply, you have to add a dummy, which we're not learning till Thursday. Okay? But in this case, this is equal because we want to meet demand. This, by the way, is consistent in transportation, it's equal, and assignment. Our customers' needs are also equal to 1, equal 1. The supply are always less than equal. Because we don't have to ship our full capacity. This is the most we could have available. But we don't have to ship them all. We're not the customers. We want to make sure our customers get it. And then the reason these are equal, because everything that goes in has to head back out. So this is equal 0, this is equal 0. However many middle nodes you have, they're all equal to 0. And every constraint has just the variables with no cost with them.
Do you ever use greater than equal to or no?
I can't remember. I don't remember using them. Maybe I can't remember. I'm sure there's a scenario, but I can't think of it right now. All right, we're going to this one. You ready? Based on the logic you learned about transportation and transshipment, apply it to this assignment network. I'm looking at node McClemens, I think. McClemens? Is that how you pronounce that? I don't know. Sure. I got a Mick in my name. I can't even pronounce that. McClemens. We don't have to assign every project leader. Yes, there are 3 available, and there's 3 clients, and we probably will assign everyone. But there's a lot of these that you have more project leaders than you do clients that need somebody. So you don't have to assign every one of them. So again, just like transportation, just like transshipment, the left-hand nodes are less than equal. But just like transportation, just like transshipment, the right-hand nodes are clients' demands. We're going to meet their demand. And this has to be equal, equal, equal. So this one would be equals 1. Now you got to erase. Ready? I'm going to do, let's do client number 1. Client number 1. What do I write for the right-hand side? What's the equality? Less than equal, greater than equal, or equal for client number 1? Equals, what number goes on the right? 1. Because it's an assignment problem. When we read it, you'll see 1 project leader to 1 client's project. The left-hand side is just like transportation, just like transshipment. How many arcs are touching that client node number 1? 3. Follow the arcs with the numbers where it's coming from, and then I know the last number will be 2, something 2, something 2. I'm sorry, not 2, 1, thank you. And you say there's 3, something x, something 1 plus x, something 1 plus x, something 1. Where is this coming from the first arc? 1. Where is this one coming from? 2. And this one? 3. You just wrote the constraint for client number 1. These are almost too easy now, aren't they? Are you ready for the story? I mean, do I need to show you? Want to do one of our project leaders over here?
Yeah.
Okay. Let's do again. Is that Carl? Okay. Is that C-A-R-L-E?
Yeah.
Okay. You ready? what's the equality? Less than equal, greater than equal, or equal, because we're doing,
Why?
Claire, I can't remember, whatever it is.
Carl.
Number 2, car. Less than equal, what's the number? 1. It's an assignment problem. How many arcs are touching that node? How many are touching this node? 3. I'm going to stare at them. Okay, there they are. Because this is coming from somewhere, I know that the first number is going to be 2. It's going from number 2 to where? Going from number 2 to where? Going from number 2 to where? You just wrote the constraint for that second project leader node right there. Pretty easy. Go ahead.
Why is it greater than equal?
Less than equal, because we don't have to, all the left hands are, we don't have to use them all, including, we don't have to assign every employee. But the right hand side is always equal, because we do have to meet the client's needs. That's our objective.
So even though we know that each employee has to be assigned to one because they're all one, like there's 3 employees and 3 projects.
Yeah, when we read the story, it'll say, we got these 3 new client projects that we have to fulfill. We happen to have 3 employees that are project leaders available that can lead each of these clients' projects. We just have to figure out which one to assign to each one. That will keep us, the story will probably say, this may represent the amount of time it would take for the project leader to do this particular project based on their expertise in the area or how new they are or something like that. And so the story is probably going to say, we have an agreement with these clients for a set amount. We bid this contract, and they're going to pay us $22,000 for this project. When we assign the project leader, our goal is to keep our costs as low as possible, because the lower we keep our costs, the more profit we're going to make on that $22,000 contract for this project. So if these are hours that will take leaders, we want to use the least amount of hours possible. So you can almost imagine the objective function. Minimize 10, this is going to be 10 hours, times x 1, plus 15 times x 2, plus 9 times x 3, and so on and so on. In an objective function, every arc is a variable that has to be in the objective function with that cost. It is the only place you put the cost, is in the objective function. Those numbers on the arc. Okay, you now have how this goes from the network to linear programming, but I need to get you from the story now to this network. Being able to draw this from the story. And that's why now we're going to go back, and I hope these stories have more meaning, that you know now what you have to do when you're reading the story. Blah, 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 blah. You read all that at home. That stuff I just passed, you read it home before you got here. Let us consider this transportation problem faced by Foster generators. This problem involves the transportation of the product from 3 plants where they make these generators to 4 distribution centers. Now, be careful. When I see the word distribution center, my mind goes to transshipment. But you nowhere in the story does it say it goes from the distribution centers then on to the client. That's why it's transportation. The transshipment problem will also mention distribution centers, but then it will say, and then it goes from there to the client. That should click you to go, oh, transshipment. We're going to have middle nodes. If it's going from somewhere to somewhere and on to somewhere else, that's what you're looking for in the story to know it's transshipment. In this case, it says we're going from 3 different plants, Cleveland, Bedford, and York, and here's their capacities that we could ship for this as a 3-month period. For the next 3 months, we're planning everything out every day for this company's shipments for the next 3 months. Here's the most we can ship. This is the most the generators will have available for the next 3 months based on production levels. And then the next slide says, and the firm is distributing these generators through regional distribution centers in Boston, Chicago, St. Louis, and Lexington. The 3-month forecast for the demand from the distribution centers are as this. So it doesn't say they're going on to somewhere else. That's why it's not a transshipment. But it does say we're going to ship to Boston, and we need to make sure they get 6,000 generators, 4,000 generators, 2,000 generators, and they got to get at least 1,500. No matter where it comes from the 3 plants we have, wherever it comes from, we got to get those numbers to those distribution centers because they're our clients in this case. Now, I'll go back here and I'll go, okay, it's coming from 3 plants. Well then, that means I'm going to need 3 nodes on the left, because that's where it's coming from. So I go, just like that. And I go, well, how much can the, and then I number them, just like that. And I kind of add stuff like Cleveland, Bedford, was this York? That's a Y, believe it or not. All right? And then I go, well, how much can they supply? Let's see, we got 5,000, I'm going to put a K, 6,000, and 2,500. I just wrote the left side of my network on this slide. And then I look at this slide and go, okay, here's where we got shipped to. And we got 4 places to ship to, so I know there's 4 nodes. And on the right-hand side of these would be however much the demand is that we got to provide. Hit me with the numbers here. We got 6,000,
4,000,
4,000,
2,000,
2,000.
1,500.
Now, I want to point something out. This is not real life. Our demand right now is 13,500, and we happen to be able to supply 13,500. Almost never is that the case. Usually demand is less than our capacity in most cases. And if it's over, then you're going to learn on Thursday, you have to add a dummy supply to meet demand. That dummy's really going to tell you who you got to back order. You may not get all, I'm sorry, I forgot the demand here. You may not get all 6,000 units to Boston because there's more demand than we can supply. Somebody, 1 or 2 of these are going to be on back order, and the dummy node on Thursday is the one that's going to tell you who gets back order. Could be 2, could be 3 of them. So now, go ahead.
Would it back order by like all 4 of them? Would it like equally back order?
Well, possibly, if that provides the lowest cost. Whatever the objective function is, it could be all 4 of them.
So will you see a constraint where they don't, where they'll need at least this many generators a lot with back order problems like that?
I'm not sure I'm clear with that question, but the answer could be yes. How's that? You're going to email me that question because I can process it right now because I got one. I think I understood what you said, and I think the answer is yes. Now, the only thing that's not here in the story are these, how much it costs to ship to each one for every item we ship. This is not, I just hit that button, I swear. I'm so colorblind, I don't know if that's red or green. It's red? I turned it on. Anyway, what you're about to see is these problems will give you a grid with the cost. Going from Cleveland to Boston is $3 for every item. Going from Cleveland to Chicago, $2 for every item. Hey. And this is the numbers you're going to place on the arcs when you get this drawing. But what really this grid is telling you, what now? Are you serious? Burn. It would have been faster for me to take a picture and email it to myself and put it up. But what it's really telling me is, can we ship? Can we ship from Cleveland? Come on. Hang on. That's as far as you can go. We believe it. Okay. You ready? When you look at this, you might be asked, hey, can we ship from Bedford to Chicago? As long as you see a number there, that's the cost for every item being shipped from Bedford to Chicago, that means we can ship there. But if this is a 0 or blank, it's trying to tell you, no, you cannot ship from Bedford to Chicago. It's out of the question. And you would not put an arc then for that shipment. In this particular case, no matter where we're shipping from, all 3 of our locations, we could ship to any one of these 4 customers. Called distribution centers in the story by customers. Because there's numbers all through here. I want to make sure you get this. Okay, you ready? Hang on. If I had a blank right there, it's trying to tell me that you can't ship what? From York to? That's what it's telling you. And you would not draw, what is York? 3, and St. Louis is, where was it? I'm pointing at. Is that 4? Was it from York to St. Louis? Okay, York is number 3, St. Louis is number 3. No arc there if that were blank. You won't put that arc in. The drawing would, the drawing would have no arc right there. That would be gone. That's what the cost grid's telling you. Where you can ship from to and the cost for every item you ship. In this case, it's every generator we ship, we have that cost. And that, now that we know that we can ship from anywhere to anywhere, throw in your arcs. Boom, 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 boom. We know there's 4 arcs, 4 arcs, 4 arcs, because we can ship from anywhere to anywhere according to that grid. Then you throw your numbers on the arc. Whatever the cost is going from Cleveland to Boston, $3 for every one. Going from Cleveland to Chicago, $2 for every one, and so on and so on. Now you've just learned how to take it from the story to the network drawing, then you go from the network drawing to the linear programming problem. All right, so just to make sure we got the full picture, you ready? I want to do node Chicago. No, look at how it's numbered, by the way. 1, 2, 3, start at 1 again, 1, 2, 3, 4. I'm pointing this out because when we get to transshipment, you cannot number like this. This is not consistent for all of these. How you number the nodes is different for transshipment than it is the others. 1, 2, 3, 1, 2, 3, 4. So now we can do our X's, where it's coming from, 2. I just said, hang on, Bailey. I just said, help me with Chicago. Start with the right-hand side. No, right-hand side.
Equals 4,000.
Equals 4,000. Hang on, man. Now, X. Wait, what's Chicago? Is it 2?
Yeah.
Say it again now. X 1 2. He said X
2,
2 2 plus X
3, 2.
3 2 plus X.
No, that's it.
What? There's only 3 of them.
Yep.
X 1 2 plus X 2 2 plus X 3 2 equals 4,000. That node constraint's done. How many constraints will we write for this problem? 7 constraints. How many objective functions? 1. Always. Always. Trick question. I want to make sure we start this objective function correctly, because it's that easy. Max or min? Min. You ready? The first variable. Give me just the variable without a cost with it. Give me an arc. X 1 1. Now what's the cost to do that? 3 plus, what's the next one?
2.
At 2 what though?
X 1 2
Plus
7
7 X 1 3 plus
6
6 X 1 4 plus, next one's a 7. Is it top of that one? Okay. 7 X 2 1 plus 5 X 2 2 plus. Everybody get it? I'm going to do this 12 times. And that's the only place all those costs go, are in the objective function. Now, when you enter this into the software, it's going to say how many arcs. You're going to say 12. It's going to say how many supply nodes. 3. How many demand nodes? 4. Then it's going to say how much are each of the supplies. And you enter node 1, 5,000, node 2, 6,000, node 3, 2,500. How much are all the demands? Node 1 for demand is 6,000, node 2, node 3, node 4. And then it's going to ask you to put in the cost for every arc, because you said there was 12 arcs. And it will say X11, what is that, 3, X12, 2. You see how you've come up with the numbers so that you get a successful output from the software? That's what it's all about, is being able to come up with the information to plug into that software, or your output means nothing. There's a sign sheet right here. Hang on. Okay, got it. Got it. Got
That's
it.
because he gave classified.
Oh.
Here we go. Hey, don't catch up on me. We're having fun. Yeah, here we go. All right. We need, whoops, I already passed the story. Here we go. Consider this transshipment problem faced by Ryan Electronics. Ryan is an electronics company that has a production facility in Denver and Atlanta. Components are produced at either facility and may be shipped to either of the firm's regional warehouses. Watch how the story tells you that it then goes to somewhere else. The company knows they ship to the firm's regional warehouses, which are located in Kansas City and Louisville, From the regional warehouses, the firm then supplies retail outlets of Detroit, Miami, Dallas, and New Orleans. Did everybody see the story go from where we're manufacturing to our warehouses to then our end retailers? That's transshipment. That's what you got to be able to see in the story to know whether this is transportation or transshipment, is that those sentences that lead you to believe it's going from somewhere to another somewhere. That's transshipment. And then you set it up just the way it reads. On the left here it says it can come from Denver, Atlanta. 2 nodes, Denver, Atlanta. Look at the numbers. Node 1, node 2. It says it goes to regional warehouses in Kansas City and Louisville. 1 node, 2 nodes. It only mentioned 2 cities. Kansas City, Louisville. Now look at how we're numbering them. We left off on 2, 3, 4. Do not, I want to tell you right now, no matter what I say, that about 10% of you are going to number this 1, 2. And then you're going to number this 1, 2, 3, 4. And that's transportation, and that's assignment, but not transshipment. And the reason is because if you identify an arc as X11, you got 1, 1 here, but you got 1, 1 here. And there's no way to know which X11 you're talking about. So you have to have a different node number on transshipment for every node. It's the only one you got to do that for. And then the story says, from our regional warehouses, we got to get to our end retailers that are in Detroit, Miami, Dallas, and this. I write 4 nodes on the right. I put the names of them. I number them. I left off at 4, 5, 6, 7, 8. I put the amount that the demand is on the right. Put the amount that we can supply on the left. I then get to my grid with the costs involved in shipping. Where's that at? Oh, you're kidding me. Come on. Oh. There'll be a grid that will say everything coming from Denver to Kansas City, $2 for each one. Everything coming from Denver to Louisville, $3. And if there's a blank there from Louisville to New Orleans, you would not put an arc here because there's no number there. Number 5 is not there. There's no means we cannot go from our warehouse Louisville to New Orleans for whatever reason maybe it can't be done.
Why don't we use the same logic we use for the nodes here in transportation and assignment?
Because if you go 1, 2, 1, 2, 1, 2, 3, 4, and I said, hey,
No, I mean, why don't in assignment? Why don't we go 1, 2, 3, 4, 5, 6?
you can.
Okay.
And you can do that in transportation.
Okay.
But as long as it's clear. He's asking, I want to make sure everybody understands what he asked, because you can do this. This would not be wrong. I'm going back to that transportation. He said, what if we number these 1, 2, 3, 4, 5, 6, 7? That's as long as I can see how you numbered them, then I understand what X, what did I say? X25.
Yeah.
Why is there a 25? I'll look at your drawing, and you numbered these 4, 5, 6, 7. You numbered them with different numbers continuing from here. That is also correct. You don't have to repeat the numbers like you see here. As long as your variables are representing the numbers you use. So with transshipment, you cannot repeat a number because there's no way of telling the difference. If this were a 1 and that's a 1, X11 could be either one of these lines, and your output will say we can't produce an output. It will say something's wrong. Doesn't make sense. So that's why you got to have every node with a certain number. This is where we'll pick up on Thursday. These are easy. I know it's a lot of information, but if you get these stuff down, they're easy. If there's no school on Thursday, I'm still going to post last semester's video so we can still do that in-class assignment, hand it in by whenever I put the date, and then we're on spring break.